Let's take a look at some of the properties of triangles. You can classify triangles a number of different ways. One way to classify triangles is by the relative lengths of the sides. So if all three sides are equal, we call it an equilateral triangle. And we sometimes use a little dash on the sides to indicate that those sides are equal length. If only two of the three sides are equal, we call it an isosceles triangle. Isos meaning same, and the skeles means legs. So we sometimes refer to the two equal sides as legs, and the third side, regardless of the orientation, we refer to as the base. And then if all three of the sides are different lengths, we call that a scalene triangle. Now, for all triangles, the sum of the interior angles is 180 degrees. And another property is that angles opposite equal sides are equal in length, equal in size. So for an equilateral triangle, all three of the angles are equal to one another, and we can use that same dash symbol to indicate that those angles are equal to one another. And for the isosceles, we refer to these as the base angles because they're the angle between the base and one of the legs, and again those are going to be equal. For the scalene, because the three sides are all of unequal length, and we can use a single, double, and triple dash to indicate that, the angles opposite them are also going to be unequal. And in particular, the angle opposite the smallest side is going to be the smallest angle. The angle opposite the largest side will be the largest angle. Now, if one angle is 90 degrees, we call that a right angle, and the triangle is called a right triangle. So, if one of the angles is 90 degrees, there's no way for the other angles to be greater than 90 degrees, since the sum of the three angles has to add up to 180. In particular, the other two angles have to add up to 90 degrees. There is, again, some naming conventions that we follow with right triangles. The side opposite the 90-degree angle, which is always the longest side, is called the hypotenuse. And then the other two sides are once again referred to as legs. And we have lots of properties that are particular to right triangles. Probably the most important one is called the Pythagorean theorem, named after the Greek mathematician Pythagoras. So the Pythagorean theorem states that the square of the hypotenuse is equal to the sum of the squares of the two legs. And we need to have some way to label this so that we can write this out a little bit more conventionally. So I'm going to start by introducing a very common labeling convention, which is to use uppercase letters to indicate the angles or the vertices. You can refer to C in this case as the vertex C, the corner there, C, or you can refer to it as the angle C, in which case we're saying the angle C is the right angle, or the 90-degree angle, and uppercase A for the vertex down here in the bottom right, and uppercase B for the vertex in the upper left. If you label a triangle this way, with uppercase letters for the three angles or three vertices, you use lowercase letters to indicate the sides. And if you're going to do this, it's extremely important to follow the convention that the side opposite the angle has the same letter, but lowercase versus uppercase. So the hypotenuse in this case would be lowercase c. The vertical leg there would be lowercase a, and the horizontal leg would be lowercase b. So we can write out the Pythagorean theorem here if we say that the square of the hypotenuse is equal to the sum of the squares of the other two sides, or the two legs, we get c squared is equal to a squared plus b squared. And we can take the square root of both sides of this by saying that c is equal to the square root of a squared plus b squared. And we'll use that to find some sides of right triangles. There are a few right triangles. Actually, there's an infinite number, but there's a class of right triangles where all three sides are integers, and we refer to the triples of integers as Pythagorean triples. So let's take a look at a few of those Pythagorean triples. If we have a right triangle with legs of 3 and 4, we can calculate the hypotenuse, c in this case, by using the Pythagorean theorem. C squared is equal to a squared plus b squared, 4 squared plus 3 squared, and that's 16 plus 9, which is 25. So if I have c squared equal to 25, then c is equal to the square root of 25, and since 25 is a perfect square, this comes out to be exactly 5. So we call the 3, 4, 5 triple one of the Pythagorean triples. And you can take that 3, 4, 5 triple and multiply each of the numbers by another number, a given number, let's say 10, and you get a triangle that is a right triangle, and it has legs of 30 and 40 and a hypotenuse of 50. And you can do that with any number you like. If you multiply all three sides by the same number, you're going to get a right triangle, and it will be an example of a 3, 4, 5 right triangle. Now, some of the other Pythagorean triples that you will come across are 5, 12, 13. So in other words, if you have a right triangle with legs of 5 and 12, the hypotenuse will be 13. There's another one that is a 7, 24, 25, and an 8, 15, 17. Now I said a minute ago that there's an infinite number of these, but these are pretty much the only ones with reasonably small numbers, with single-digit numbers. And so you're going to see them a lot on geometry questions in math textbooks and on exams and contests when they want the sides of triangles to be integers and not irrational. See if I can get that window to stop popping up. All right. So let's take a look a little bit at trying to find some other missing sides, especially when the sides are not integers. So let's say we have a right triangle with legs of 2 and 3. So here's 2 and 3, and again we can label our triangle. So we're trying to find c once again, and we know that c squared is equal to 2 squared plus 3 squared. Well, that's 4 plus 9, which is 13, and therefore c is equal to the square root of 13, which is an irrational number. So that's the best we can do if we want to represent it exactly, and if we want, we can use a calculator to get a decimal approximation. And we know that it's going to be somewhere between 3 and 4, because 3 squared is 9 and 4 squared is 16. And it's not a big surprise that it's bigger than 3, because we expect the hypotenuse always to be bigger than any of the two sides. It has to be the biggest side of the triangle because it's opposite the biggest angle. Let's try another one, this time where we're missing a leg. So if we have a right triangle with a hypotenuse of 7 and one leg of 5, this time I'm not going to label it as ABC. I'm going to label the missing leg as X. So once again, it's important to write out the Pythagorean theorem. I usually like to write it out exactly the same way every single time. So the square of the hypotenuse, in this case 7 squared, is equal to the sum of the squares of the other two sides, or the two legs. And so I end up with 7 squared is equal to x squared plus 5 squared. So if I want to solve for x, I need to get x squared on its own first. So I'm going to subtract 5 squared from both sides. And then I can figure out what 7 squared is 49, and 5 squared is 25. and I get x squared equal to 24. So if I know that something squared is equal to 24, I can take the square root of both sides, and I can get x equal to the square root of 24, which is almost 5, because the square root of 25 would be 5. And you can simplify the square root of 24 because it's the product of the square root of 4 and the square root of 6. And the square root of 4 is just 2. So another way to write the square root of 24 is as 2 times the square root of 6. And again, of course, you can always pull out a calculator and get a decimal approximation, and it's going to be something between 4 and 5, close to 5. All right, so there are a few so-called special right triangles that are special not necessarily because of the side lengths, but because of the angles. One of them is an isosceles right triangle. So an isosceles right triangle has two sides the same length. So the special right triangles. An isosceles right triangle, because two sides are the same, those two sides have to be the two legs, because the hypotenuse is obviously the longest side here, and so we can't have two sides the same length as the hypotenuse. So if we have the legs, let's say, as 1 and 1, the angles opposite them are equal, and they have to add up to 90. So they must be equal to 45 degrees. And so sometimes this is referred to as a 45, 45, 90, or an isosceles right triangle, or it's sometimes referred to by the length of its sides. And again, we can use the Pythagorean theorem to find the length of the hypotenuse, c in this case. So c squared is equal to 1 squared plus 1 squared, which is just 1 plus 1, or 2, and therefore c is equal to root 2. And so sometimes this is referred to as a 1, 1, root 2 triangle. Now once again, you can create similar triangles by taking that ratio of sides, 1, 1, root 2, and multiplying it by any number you like. So for instance, you can multiply it by 5, and instead of the legs being a length of 1, they would be a length of 5. And the hypotenuse, instead of being a length of root 2, would be a length of 5 times root 2, or 5 root 2. And so this is another 45, 45, 90 triangle. The other special right triangle is half of an equilateral triangle. So if you can imagine having an equilateral triangle, the other half of which would be over here. The shortest leg here, when you first explore it, is typically given a length of 1. And you can see that by looking at the equilateral triangle from which we're taking this, the hypotenuse here would be twice that length, which would be 2. So then the question is, well, what are the angles? Well, again, if it's an equilateral triangle, this base angle down here would be 60 degrees, which means that the angle on the top here has to be 30, because the two angles aside from the right angle have to add up to 90. And now the only thing missing is the length of that long side, the leg opposite the 60-degree angle. We know that it's going to be greater than 1 because it's opposite an angle that's bigger than 1. And we know that it's going to be less than 2 because the hypotenuse has a length of 2. So we can use Pythagoras to figure out what that length is. I'm not going to label it x because I'm going to run out of room there, but let's just say we have x as the missing angle. And we know that the sum of the squares of the two legs, so x squared plus 1 squared, is equal to 2 squared. And we end up with x squared plus 1 equals 4, and therefore x squared is equal to 3, so x is equal to the square root of 3. And once again, this triangle is referred to either by its angles, 30, 60, 90 triangle, or as a 1, 2, root 3. Now, the 1, 2, root 3 can get a little confusing because we don't really have a good intuitive grasp of how big 2 is, or rather root 3 is, whether it's bigger or smaller than 2. If you think about it just for a second, you can realize it's smaller than 2. But it's perhaps a little bit better to refer to this as a 1, root 3, 2 triangle, but it doesn't roll off the tongue quite as nicely like that. Now, let's talk a little bit more about different ways to label triangles, because there are some other ways to label triangles and angles, the angles in particular. So let's just have kind of a generic triangle here, and we will label the vertices, or the angles, ABC. The sides opposite those angles we'll label also ABC, but with lowercase. And again, the side opposite angle A is lowercase a, the side opposite angle B is lowercase b, and the side opposite angle C is lowercase c. Now, it's possible to use segment notation to refer to the sides. So for instance, we can refer to the segment AB, and you can just write it as AB, or you can really be a little bit more formal and you can put the bar over it. So that's the line segment AB, and based on our diagram you can see that's very clearly lowercase c. And so these are equivalent ways of labeling. We can also, of course, have line segment AC, and that would be the same as lowercase b. And we can also have line segment BC, and that would be the same as lowercase a. The angles also we can use the ABC and have a more formal notation. So for instance, we can refer to angle A with this little angle symbol. And if we really want to be careful about this, we can call angle A angle BAC. So you can think of the angle being formed by the two line segments BA and AC. This seems sort of overkill, but in more complicated diagrams it becomes necessary, because sometimes you may not be able to know what's being referred to if they refer to angle A, and therefore you need something a little bit more specific. So similarly, angle B would be the same as the angle ABC, and the angle C is going to be the same as angle ACB. The order is not terribly important. In other words, I could have written this as BCA, but one thing you should notice is that these angles correspond to that middle letter, all right? And so if you're looking at three letters, BAC, and you're not sure what angle is being referred to, just make sure that you're referring to the middle letter. So BAC is going to be angle A. But again, we're not really going to see that notation unless the diagram is a little bit more complicated. There is yet another way we can refer to the angles, and that's by using a variable. And typically, when you're using a variable to refer to angles, we use Greek letters. So Greek letters like theta, alpha, beta, etc. Not always. We can use letters like x, y, and z, but theta, alpha, and beta are quite typically used for angles. So let's say we want to make angle A theta. Well, we could just refer to that there as a theta. And if we made angle B equal to alpha, then we've got an alpha there, and then angle C equal to beta, so we've got a beta there. So lots of different ways to refer to angles, depending on the context. Now, one last really important thing to do with triangles, important because it comes up quite frequently on these sorts of exams, is thinking about the logic of the sides. So if you're given two sides of a triangle and you're asked about the third side of the triangle, you've got to think about this a little bit carefully. So let's say you were asked to construct a triangle with sides of 3 and 5. How long is the third side? So this can get a little bit confusing. It's nice to actually play around with some lengths if you have some straws and you want to cut them up, you can play around with that. You can also use some software like GeoGebra. So GeoGebra is freely available on the net. You can download it, or you can use a web version of it. So what I've done is I've set up here a demonstration, and imagine that you had two sides. Let's say this one was a length of 5 and this one over here was a length of 3. You can see that you can't have that third side be too long, otherwise you're never going to be able to sort of close this triangle up, and these two sides of 3 and 5 are just sort of going to flop around and they're never really going to connect whatsoever. And so for that reason, that third side cannot be longer than 8. In other words, it can't be longer than the sum of the two sides, 3 and 5. And if it were exactly 8, then we wouldn't really have much of a triangle, because the only way to connect them would be to have these two sides lying perfectly flat, right? We could have them, in such a way that they just barely join up like that. And that's not going to be much of a triangle. So we actually need to have that third side be something less than 8. And in that way, you can see we can construct a triangle with sides of 5 and 3, and then the third side would be less than 8. So we can sort of summarize that, if you like, by saying that one side can't be longer than the sum of the other two sides. Now, we can go to the other extreme, if you like, and think about, well, what if the 5 is the longest side, and the 3 we're trying to connect with another side to make a triangle? And so if we go back to this GeoGebra example here, imagine now that this horizontal leg is the 5-unit long side, and the one on the left here is the 3-unit long side. Well, once again, the same property holds. That longest side, 5, can't be longer than, so the longest side, 5, can't be longer than the 3 and the other side put together, which means that the other side, this small side, has to be at least 2. If it's any smaller, then those two smaller sides are not going to add up to 5, and we're going to have a problem. So we can essentially summarize this by saying that the 2 has to be the smallest possible third side, and the 8, the sum of 3 and 5, has to be the largest possible third side. So that third side's got to be somewhere in between 2 and 8. If it's exactly 2, again, we're just going to have a flat line. We're not going to have much of a triangle. If it's exactly 8, same thing. So as long as that third side is somewhere between 2 and 8, then we'll actually be able to construct a triangle.